My topic for today is long mode and what it has in common with legacy modes, 32-bit mode to be exact. Ever since I was first implementing long mode encodings into my assembler, I noticed that it was designed in a specific way, a bit different how earlier 32-bit mode versus 16-bit mode worked. First of all, default operand size in long mode is still 32 bits. One would think that this would allow to simply run unchanged 32-bit code in long mode. And sometimes that is true, but there is more to it. In fact, the defaults are a bit more complex than just preserving 32-bit as default. We are going to take a look at this later. For now, I'm just going to write a few things down. Default operand size is 32-bit. This means that instruction encoded the same as in 32-bit mode would be exactly the same instruction in long mode. Just like in 32-bit mode, 6-7 prefix switches to 16-bit, and a new prefix rex allows to switch to 64 bits. This is going to affect instructions like this one. Another important detail, very important, is that when an instruction modifies a 32-bit operand, it clears the upper part of register. This was strange when we first noticed that this is unlike 32-bit mode on earlier CPUs, where never before it was this way. When you modified a 16-bit register, you did not modify upper half of 32-bit register. But when I looked in detail at how long mode encodings work, I realized that this was a very wise move. Turns out that thanks to this detail and a few more that I'm going to talk next, it is really possible to run sometimes unmodified 32-bit code in long mode. Because as opposed to default operand size, default memory addressing is 64-bit. Oh, I made a mistake. This was supposed to be 6.6, not 6.7. Here it is 6.7. .6.7 prefix applies to memory addressing size, and it changes to 32-bit in this case. Therefore, this instruction in 32-bit mode was encoded like this instruction is encoded in long mode. Because default is changed to 64-bit, the addresses become promoted. This means that when we have instruction that uses memory and has no prefixes, the 32-bit size of operand stays unchanged, but 32-bit addressing is promoted to 64-bit addressing. As you can see in that small routine I have once written as a demonstration of the concept, this allows to have an unchanged binary code written for 32 bits and operate in long mode and still use pointer provided as one of parameters to the function perhaps. And this pointer could be full 64-bit. Now, when a 32-bit code run in long mode this way, calculates pointers on its own, it may use these pointers even though addressing is going to use 64-bit registers, but thanks to this bit, that upper half of 64-bit register is cleared, it is still possible to use this addressing. Or perhaps something mixed. Let's say that RBX is our input register. A full 64-bit address. And then in our routine we calculate some additional offset perhaps inside an array. We do some calculations. At the end of this, RCX is going to be zeros in upper half and ECX in lower half. And now we have instruction that from 32-bit point of view would be this instruction, but in long mode the same opcode is going to be decoded as RBX plus RCX. But this is still going to work. We have not touched the base address, it stays 64-bit. And our offset, even though we calculated it as 32-bit, it is automatically 0 extended to 64-bit RCX. So this addressing is also going to work in long mode. And this design allows to write code like this one that can run in 32-bit mode, and unchanged binary can run in long mode and still do the right thing even with long addresses. There are also some special cases where 64-bit operand is default. Push and pop, also call and jump. These are all related because default unit on stack is 8-byte, 64-bit, and so the address that call stores on stack also needs to be 8-byte. And everything I have written down here is in fact mostly enough for the purpose of refurbishing 32-bit code of FASM to run in long mode. Something I have done some time ago for FASM1. Oh, what about RSP? We are going to get to this in a moment. In general, where you had instruction that accesses stack in this way, then because in long mode default memory addressing is 64-bit, the same instruction would be interpreted as operating on such addressed stack. So it would still work, as long as you don't modify ESP register. Because if you try to do something like this, then you clear the upper half of RSP, and obviously you may break the address if it's long. And we are going to see this in practice in a moment. This is a 64-bit version of FASM, but this is a trick. I have never really made a version of FASM that would be truly 64-bit. I have just made some tricky macros and wrappers so that the same code could run in long mode and still do its things, do the right things. Here are the macros I used. You can see one of the first things I did was to redefine ESP to RSP. Now here are macros that redefine push and pop instructions. These macros are called here. This is a complexity of FASM1 macros. We do not need to delve into this right now. This is just to handle multiple arguments to push and forward everything to this pushD macro. So this pushD macro is really the only one that is important for us right now. And what I did in case of FASM1 was to redefine push and pop so that they would emulate 32-bit push and pop and preserve the stack layout. Because FASM1 uses stack very often to lay down some structures there, or just store registers in a particular order and then access them through offsets. For example, I might do something like do some pushes and then access one of the stored values this way. And because I had no easy way to adjust the offsets automatically, the simplest solution was to make these pushes preserve the layout. Therefore, instead of making a native 64-bit push, this emulates a 32-bit push. So it adjusts RSP manually and stores the values on the stack with MOVs. And pop does the same things in reverse. Now the other thing is, I have just mentioned how it is possible for unchanged 32-bit code to use 64-bit addressing. In case of FASM, I just reassemble entire code, and when I reassemble this code in long mode, it simply starts putting 6-7 prefixes everywhere. So FASM core still uses 32-bit addresses everywhere, and in addition to that it uses a lot of 6-7 prefixes. This is why the code grows. You can see, compared to 32-bit code, it is about 12 kilobytes more. I also had to modify jump and call in some places, because call and jump also have 64-bit as default, and FASM1 sometimes jumps to memory operand, for example, or register that is 32-bit. I also had to emulate some of the instructions that are no longer available in long mode. Now, what I would like to try is to do the same for FASMG. But in this case, everything is a bit different. FASMG was already written with that in mind, that I would do tricks like this in the future. So FASMG is written in a lot cleaner way. For example, let's look for this kind of accesses. Oh, nothing here. Yeah, just a single one. For example, as a rule, in FASMG I never use ESP with offset. I only do push, pop, or access top of the stack. This makes it neutral from the point of view of stack unit size. Therefore, all these push instructions could stay on binary level unchanged and then become 64-bit interpretation of the same binary code, and everything should work, because for FASM code only 32-bit portions matter, and this sequence of push and pop would anyway just store and restore additionally upper half of register, which doesn't matter for us anyway. And is cleared most of the time, because when we keep modifying these registers, the upper halves are constantly getting cleared. And this, thanks to Intel architecture being little endian, well, this is one of the cases where we can see why little endian has advantages. This will work correctly, because when we store 64-bit register on stack, then its lower 32-bit part is going to be available at this address of the top of the stack. Well, okay, I need to correct myself. Little endian is only better here because of how the stack is implemented. If we had if we had stack growing in the other direction and addressing well, it's still, with big endian it's not so easy to make something analogous, but I think it is possible to make something a bit similar. Just reverse everything. So, but perhaps also memory addressing would need to be reversed. I mentioned this because for someone learning Intel architecture, it is sometimes not so obvious why the stack layout is the way it is. When we put new thing on a stack, so that we lay more elements on the top of stack, the address of the top of stack actually moves downwards. It becomes a smaller address. Alright, so let's write it down. FASMG. We can leave push pop unchanged. Oh well, the stack growing downward. This really is, as demonstrated here, this really fits nicely with Little Endian architecture. Because then the stack pointer simply becomes an address of the lowest byte of what is on top of the stack. Well, imagine that this was the opposite, that ESP was... Wait, if the stacks was growing upwards, then ESP would have to be an address probably after the element that was put on top of the stack. So then when you did push EAX, then to access EAX you would have to do it this way. Well, I think it would be clunky. I really think that the way it is with stack growing downwards and Little Endian, this really, everything nicely fits together. If we leave unchanged push and pop instructions, unchanged binary codes, then this in fact promotes the register size. So push EBX becomes push RBX. But what about memory? If we have such instruction, this pushes 32-bit value. We cannot promote it to push quad word EBX. Well, for example, this double word might be last double word in page and next page might be inaccessible, then this instruction would generate exception. And it's even worse with pop. Because then with pop we would overwrite another double word, something that was after this variable in memory, and probably break something. So this is not the way to go. We need to handle this specific cases. We can use a register. In long mode we have 8 bonus general purpose registers. Obviously 32-bit code did not use them, so we are free to use them however we wish. We can use them for temporary storage. For example, we can do something like this. And then push entire R8. Upper half has been cleared because of this 32-bit access. And then to restore this in the opposite direction. Okay, so this is unchanged binary code, and this is case where we need to change some instructions. So it is not that we can run this entire 32-bit code unchanged in long mode. Some instructions need correction. And we are going to promote sizes of registers using for addressing just to avoid the 6-7 prefix. Then we are also going to have some instructions like jump to double word. In long mode we have no 32-bit jump available, so we need to make a 64-bit value to jump to. Again, we can use a temporary register. And jump like this. This is a plan. Now to apply these changes, I'm going to prepare a special version of FastG. Let's call it raw. Let's take a Linux version and cut it down. I want to make first cut down FastG to cut everything that is dependent on operating system. Just leave the basic 32-bit code so that we can then apply the tricks to it and look at raw code, how much is it changed, and worry about OS layer later. This first section is to detect whether this is assembled with FASM1 or FASMG and include some files for either case. We are going to not support FASM1. Because to do these tricks properly, we need the power of FastG macros and implementation of instructions set in form of macros. Self-host, this is for FastG. We include the instruction set, so this is okay. This is for this multiple operand syntax of push and pop. We don't need format. Well, we are just going to set it to 32, no, 64. Let's start with 32. First we just cut down it to raw code. Invoke is only for system calls. This everything is for imports, so we can cut it. Okay, this is the minimum. No format, no imports. This is for OS layer, no segments. Can we leave something here? Oh, maybe just a minimum. Ah well, let's cut down the command line interface entirely. We can recreate it later when we need one. These are labels that are needed for core. No segments, no command line messages. Okay, this is pure core, and system are the, again, functions provided by OS layer. We are going to need them in 64 bits later. For now we can just cut them. Leaving the labels so that the source assembles. You may notice that this is in fact a good preparation for if you wanted to port FastMG to another operating system, perhaps your own operating system, then you have to re-implement all these functions and re-implement the command line interface here, or perhaps a graphical interface instead. Alright, let's try whether this assembles. Oh, I did cut too much. Yes, this is something that core needs because of console functions. It needs to know what kind of line termination it should make. Great, disassembled. This is a raw code of FastMG with no operating system interface implemented at all. Just labels pointing to nothing. Next step is going to try to assemble the same in long mode. Of course, we have an error with push, because in long mode there is no 32-bit push available. Push needs to be 64-bit. So we had to apply this planned change. Let's look for how this instruction is implemented. Well, we have several options how we can do this. One would be to modify this macro here, this large macro inside. The other option would be to just make a wrapper for push. This might be a simpler variant. So first, when operand is register, we need to promote it to 64-bit register. We can make some simple, perhaps create a table. Oh, okay, this needs to be parse. And now we need to recognize it with match. Let's add a colon here. So when this is a register and this needs to be also case insensitive. Let's see if it does something. Yeah, this time it errors on pop instead of push. So we need to make a similar thing for pop. Great, push and pop mostly works, but we also have this case, and in fact when something is not a register that we are promoting to 64 bits, then we can assume that this is a 32-bit value. And next we have jump to handle. We just need to detect a memory operand as jump normally. And now we see that we have a problem of some jump becoming a jump out of range. This is because our code is growing, but it should not be growing so much. The main reason why it is growing so much is because of 6-7 prefixes. Therefore we need to get rid of the 6-7 prefixes, because I already mentioned that we can use 64 bits addresses instead of 32-bit with no problem. The upper parts of registers are cleared anyway. How can we get rid of these 6-7 prefixes? Well, let's take a look at macros and let's find the part that we can overwrite. This time we are going to take this huge macro and just tweak it a little. When we are in long mode, we use 64-bit addressing even though the registers that are written down are 32-bit ones. Oh, we have a jump to register still to handle. And I remembered another thing. One more thing to add here. A pure displacement memory addressing is no longer available in long mode. The same binary encoding is going to be interpreted as RIP relative addressing. But this is something that Phasm is going to handle for us anyway. In long mode, Phasm automatically generates RIP relative addressing every time you just use a label here. A label that has no registers in it. As for this jump, what can we do? Let's just jump to racks. Oh, we can promote it just like push and pop, in fact. Under the assumption that upper half of register is cleared, but it should be. Since we jumped to EAX, we must have had set up EAX in some way, and any instruction that modify EAX did clear upper half of this register. So the assumption should be sound. And now we have the same thing with call instruction. Let's do it fancy way with iterator. Great, this assembles finally. Well, I don't know, I might be ending soon. Oh. I don't think we have enough time today to write entire Linux or Windows interface for 64 bits. So we may continue next time. At least we have this code, raw code assembling as a long mode code. Let's take some tool and take a look at it. This is the code. Well, you can see where we use a label for a variable, fast automatically generated RIP relative addressing. This instruction, you can see that we promoted it by avoiding 6-7 prefix. So EDI plus EAX became RDI plus RAX. Which should not be a problem because upper halves are cleared. Can we find some push? Oh, here it is. Promoted push. Most of this code is going to be completely unchanged from 32-bit version. We are just reinterpreting instructions with default sizes as used by long mode. Now the question is, would you like me to write OS layer, this system implementation next time? Or would you prefer some other topic? The most serious problem here is memory allocation. Because we have to allocate block that has a 32-bit address. Because obviously the entire core of FastG, even though we adapted the code to run in long mode, it still uses structures with fields for pointers that are 32-bit. This is not something so simple to adjust. Yeah, but you see, FastG requires realloc, and unless we are willing to write our own realloc implementation with syscall brk, then we have to use libc allocation and realloc. And I'm just not sure if that memory alloc is going to always allocate 32-bit addresses. Because malloc uses syscall brk, but also syscall memory map sometimes. And this second one might sometimes return 64-bit address, I'm not sure. Okay, so we might have a problem when malloc calls mmap, right? Yeah, then we cannot simply use malloc, because FASM sometimes allocates large blocks and malloc is going to try to use mmap then. And this is going to break down with too large address. Yeah, of course, we can... At first we can write something very simplified here and just as a proof of concept get it running, and then after we get it running we may worry how to make a fancy malloc here. I would gladly write some customized malloc because this would give me an opportunity to use these hints. Because for now all versions of FASMG have these 3 labels point to exact same function, but they may be 3 different functions, each one optimized for a specific purpose. Oh, for example, malloc fixed would be an ideal place to use mmap, but since mmap returns too high addresses anyway, then we cannot do it this way. Not that this matters very much, because I managed to optimize FastG that in such way that it does not really depend much on the speed of memory allocation routines. The bottlenecks are elsewhere. So if we make a slow memory allocation, that is not a problem. The problem is that it might not only be slow but also wasteful. We would prefer it to be not wasteful. Of course, realloc is always going to be a bit wasteful. But for first naive version, we could make just realloc that does not really free memory. Just keep allocating new memory at the end of the block, and this would be enough to just get things going as a proof of concept. Alright, so we are going to make elf with no dynamic imports, because since we are going to implement malloc ourselves with only 6 syscalls, then we no longer need libc, we just need syscalls. So this should be a relatively plain elf version. And most of these functions can be in fact copied from FASM1. Because FastG uses an interface that is similar to one used by FASM1. And many of these functions were already implemented as this kind of 32-bit to 64-bit wrappers. So we can just copy them from FASM1 and just make sure that everything is as in specification. Perhaps tomorrow then. As I feel we are over time today already. Tomorrow we may get back to this and implement all these functions and adapt a command line interface and try it out if it runs as 64-bit ELF in Linux. Yes, I wanted it to be this way. I wanted to make something more ambitious this time. With a real substantial result. Oh, here we have a converted jump. And we are still using just one of bonus 8 register. We still have 7 additional registers that we can use for some additional purposes. A nice thing to have. For example, we might replace some memory variables in FASMG source with bonus registers. Because we have instruction sets in form of macros, we really have a lot of control over everything. We could replace this macro . And perhaps parse an operand that would look like this. Well, yes, we would have to move this to another. Oh wait, we can use this previous value. No problem, because we are overwriting macro simply. If we do it this way, we can Let's do this for trace mode, for example. Then when we have such operand, this is going to become this and should be catched by this macro. It did not catch it. Oh, I see. This should be a first match in sequence, not a second one. We need to catch it early. This is the last thing I'm going to do today. Well, this is a bit strange. Why did it not catch it? Well, it did not. Oh, you're right. Was this the error? We did break DB definition. Oh well, of course. We would have to somehow remove this definition then. Just a small trick to not have modify the core files. Ignore the argument. Okay, and let's see what this instruction became. Oh wait, this is not the file. I'm in a different place now. Silly mistake. Okay, so this instruction is now mov R9B AL. So we could use tricks like this to replace some memory operands with registers, because we have some bonus registers. If we identified some variables that are frequently accessed, then we could optimize them this way and perhaps gain something in terms of performance. But that's just for the future. Alright, then tomorrow we are going to try get this running. As for today, thank you for watching and see you tomorrow.